Okay, so in this next video on systems of linear equations, we're going to start looking at some systematic methods for solving a system of equations. Now, in the previous videos, we saw that there are certain things you can do to manipulate the equations to try and tease out a solution, right? Now, there are a few things we can do that we can all agree are not going to change the outcome as far as solving a system, right? So the first one says, well, obviously it does not matter. The order in which we write down the equations is not going to matter, right? So you can swap the positions of any equations in your list of equations. It's also true that if you multiply both sides of an equation by a constant, as long as whatever you do to one side you do to the other side, right? Multiplying everything through by a constant, that doesn't change the equation either. And we saw that, one of the things you can do to try to eliminate one of the variables is you can add one equation to another, or maybe you need to first multiply one of the equations by a constant before you add it, right? So you can combine equations in that way, right? So if you have two equations and you add the left-hand sides from one equation, you add the right-hand sides, if the two equations were both balanced to begin with, then adding two equal things is going to give you the same result, right? So you can combine these two equations. It turns out that these are the only three things you need to do to solve any system of equations, okay? So here's an example, right? We could label these, let's label these 1, 2, 3, okay? So I could do a couple of things, right? I could do, I'm going to keep 1. I'm going to kind of transform this to a new system. So it's going to do the same. So the first equation is going to stay the same. X plus 3y minus 2z equals 4. Then I'm going to take the second equation, but I'm going to subtract off the first equation. So x minus x gives me 0. Minus y subtract 3y gives me minus 4y. There was no z here, but then I'm subtracting minus 2z, so that's adding 2z. So minus 4y plus 2z is equal to minus 2 subtract 4. I get minus 6. I'm going to take the third equation and I'm going to subtract off 3 times the first equation. Okay, right, again, my goal is I'm trying to get rid of the x. So 3x minus 3x gives me that 0 I'm looking for, right? So if I multiply by 3, just so we kind of keep track, 3x plus 9y minus 6z equals 12. So I'm subtracting those from the third equation. So 3x minus 3x, 0 minus 4y minus 9y minus 13y. Z minus 6z, that gives me plus 7, right? 1 plus 6 gives me 7. And finally, I have a 0 here, and then I'm subtracting 12. So 0 minus 12 gives me minus 12, right? So now what I can do is I can say, okay, you know what? Let's ignore the first equation for a minute, and let's focus on these guys. Okay, let's call these. So these are going to be some new equations. So let's label these guys maybe 4 and 5, right? So maybe the first thing I'll do here is I'm going to do minus 1 over 4 times equation 4, and that's going to give me y minus 1/2 z is equal to 3 over 2 if I multiply everything by minus 1 over 4, right? And let's label that guy, so I guess that's going to be 6. And now I can take equation 5 and I'm going to add 13 times equation 6, right? Because 13 times equation 6, I'm going to get 13y minus 13 over 2z is equal to 39 over 2. Okay, And now if I combine that with 5, what do I get? Well, the z's go away, 13, or the y's go away, 13y minus 13y, they're gone. I've got to do this, right? 7z plus minus 13 over 2z. 7 is 14 over 2, so this gives me 1/2 z. So I simply get 1/2 z equals, what do I get when I add on the other side? I've got minus 12, and I'm adding to that, I'm adding 39 over 2. So minus 12, that's minus 24 over 2. So that's going to give me 15 over 2. So I get 1/2 z is 15 over 2. And now I'm in business because that's one equation, one variable. I can solve that, right? So I get, what do I get? I get z equals 15. Let's plug that into 6. Okay. Y minus 1/2 of 15, so 15 over 2, is equal to 3 over 2. So this tells me that y is equal to 3 over 2 plus 15 over 2. That's 9. Okay. So now I plug that all the way back into the first equation. Not just the value for y, but also the value for z. X plus 3 times 9 minus 2 times 15 equals 4. That tells me, okay, so that's x plus 27 minus 30, so x minus 3 equals 4, x equals 7. Okay, so I've come up with values. X equals 7, y equals 9, z equals 15, and I could, if I wanted to make sure that I didn't mess anything up, one thing I could do is I could take those values, I could plug them into any one of the 3 equations I started with, and I'm going to leave this as an exercise for you. Exercise. Verify. Verify that this works, right? So take those 3 values, x is 7, y is 9, z is 15. Try them in any one of the 3 equations we started with and make sure that it works for all 3, okay? That's how you know that you've solved the system, right? Once you plug them back in, then you know for sure you did your job. Okay. Now it's a bit of a mess, right? One of the things that's really messy here is carrying along those variables, right? We notice as we go that the thing that doesn't really matter, like the names x, y, z, don't really matter. They're almost kind of placeholders, right? The things that we really care about here are these numbers, the coefficients. Those are the things that we're working with. So what we do to kind of make our lives easier is we just drop the variables. We write everything down. We just keep the numbers. But we got to keep track of where those variables were, right? We got to remember where those numbers came from. So what we do is we write things down in what's called an augmented matrix, right? So we organize things into rows and columns, right? So we see that the first row corresponds to the first equation. The second row is the second equation. The third row is the third equation. The first column are the coefficients for x. The second columns are the coefficients for y. The third column, coefficients for z. And these guys, well, those are the constants on the right-hand side. Okay? It's going to be much easier to work with this matrix than it is to work with the original system. And we're going to see that we're going to be able to write down an algorithm that allows us to always take an augmented matrix like this and reduce it down to a simple form where it's very easy to read off the solution to the system. So there are 3 skills that you need to learn as you work through systems of equations. The first is simply going back and forth between a system and an augmented matrix, right? If I give you a system, you want to make sure you can immediately jump to this augmented matrix. If I give you the augmented matrix, make sure you know how to write down the corresponding system. Okay, that's pretty straightforward. The next skill set is taking this augmented matrix, reducing it down to a simplified form. We have to say what that simplified form is. We'll give you an algorithm for that. You'll learn how to do it. The last thing is, once you get down to that simplified version, how do you read off the answer? You want to make sure that you can read off the answer quickly. So we'll get to all of that in due course. Okay, so those elementary operations, those things that we could do to our equations, those correspond to things we can do to the augmented matrix, right? If I had chosen a different order in which to write down my equations, think about here, if I had maybe put the second equation before the first one, I would still have the same system, right? I'm just writing down the equations in a different order. But that would correspond, if I swapped these guys here, I would end up swapping the corresponding rows in the augmented matrix. So one of the things that we want to allow ourselves to do is swap two rows, right? So we can interchange the positions of any rows in the matrix. Be careful when you do it, right? You don't just swap these guys, you got to remember the guy on the other side of this bar here, right? When you swap equations, you got to move the constants on the other side of the equal sign as well. You don't just move the variables, right? So when you swap rows, you swap the whole row. And we know that we can also multiply an equation, both sides of an equation, by a constant. And, in the augmented matrix, that corresponds to just multiplying all the way across a row by some constant, right? So we could, for example, take maybe the second row here, multiply everything by 3. We would get 3 minus 3, 0, minus 6. We multiply by 3 all the way across. And the main thing we do, the main way that we kind of simplify is we combine equations to cancel variables, and we do that by multiplying an equation by a constant and then adding that to one of the other equations, and that corresponds to multiplying one of the rows by a constant and then adding that to one of the other rows. So these three row operations, and these often are if we want to refer to them by type, this is often called a type 1. This is often called a type 2. This is often called a type 3 row operation. With these three types of row operations, we can reduce any augmented matrix to a simplified form where we can read off the answer to our system. Okay, so here are some basic examples. Okay, I'm gonna kind of jump ahead quickly so we don't make the video too long, but you can always pause here at this slide and peruse these examples. Okay, in the first one, we see what happens when we swap the two rows, right? So the original row 1 becomes the new row 2. The original row 2 becomes the new row 1. We're just interchanging the two rows, right? I could multiply across one of the rows by a constant, and in this case, I've multiplied by 1 over 3. Right, so dividing by 3 is like multiplying by 1 over 3. So I multiply everything by 1 over 3. That's something else I can do. And I could multiply one of the rows by a constant and add it to another row. So here what I've done, this row operation, I've multiplied row 1 by minus 1, and I've added that to row 2, and that gets me to here. So I'll leave you to pause and check that that's exactly what happens in that row operation. Okay? Now, and by the way, just for consistency, I guess, with the textbook, the notation you'll see in the textbook, they write things the other way. They'll write this as 1/3 row 3 becomes the new row 3, and they'll say that row 2 minus row 1 becomes the new row 2. They just kind of write things, the other way around with respect to this arrow. So I'll try to stick to the same notation as the book. All right, so we kind of, when we were solving this system, we kind of played around. I didn't solve it exactly the way we see it here, but we can reduce things down, get to sort of a simpler system, right? And so we got down to that z equals 15. We plugged it back in to solve for y. Then we took the y value to solve for x, and oops, that should be a y there. Right, so we can reduce all the way down to, this would be the simplest possible system: x equals 7, y equals 9, z equals 15. Right, we can't reduce beyond that. We've just got the answer staring us in the face. So how do we do that if we were working with the augmented matrix instead? So if we've got our augmented matrix, then what I would do here is I'm going to start out by, so the first thing I'm going to do is, well, it's nice to have these 1s, right? Because with a 1 you can easily use a 1 to get rid of the things sitting below it. We'll see that this is kind of the first step that we do. So we could take row 2 minus row 1 and make that the new row 2. While I'm at it, let's also take row 3 and subtract off 3 times row 1 and make that the new row 3. So I'm doing two steps at once, but each one involves a different row, so I don't have to worry about these conflicting with each other. So I haven't changed the first row. It stays as it is. So now I'm doing row 2 minus row 1. So I do 1 subtract 1 gives me 0. Minus 1 subtract 3 gives me minus 4. 0 subtract minus 2 gives me plus 2. And minus 2 subtract 4 gives me minus 6. Now, row 3 minus 3 times row 1. So 3 subtract 3 times 1. So 3 minus 3, 0. Minus 4, let me write that one out. Minus 4 subtract 3 times 3. That's minus 4 minus 9. That's minus 13. That minus 13 goes there. Okay. Next up, 1 subtract 3 times minus 2, that's 1 minus 6, so that's 1 plus 6 gives me 7, and then I get a minus 12. So I get down to there. Okay, so where do you go from here? Well, one of the options would be to kind of proceed as we did before. So if we want to follow the example we did before, there's kind of, there's no one right way to do this. So one way you could do this is you could do minus 1 over 4 row 2 and make that the new row 2. Okay, that's what we did when we solved it before. Some people might not like doing that because fractions are going to come into the picture. The other way you could do this, if you don't like the fractions, is I'm going to do this. I'm going to do row 3 minus 3 row 2 and make that my new row 3. Why do I want to do it that way? Well, let's see what we get. Okay, 1, 3, minus 2, 4, 0, minus 4, 2, minus 6. Okay, 0. So minus 13 minus minus 12 gives me a minus 1. Okay. 7 subtract, so 3 times 2, 7 minus 6 gives me a 1. And then minus 12, I'm going to get a 6 there. Okay. So I get down to there. You could do it the other way if you want, but here's another way to do it. So then one thing I could do, and let me just kind of, I'm going to sort of sneak in a row operation here. I'm going to do row 3 goes to, I'm going to change the sign on row 3. So that's going to become a plus, minus, minus. Okay. Then I'm going to do, the next thing I'm going to do is I'm going to exchange row 2 and row 3. 1, 3, minus 2, 4, 0, 1, minus 1, minus 6, 0, minus 4, 2, minus 6. And where do we go from here? Well, now I'm going to use this 1 to get rid of the 4. Okay. So I'm going to go row 3. I'm going to go row 3 plus 4 row 2 is my new row 3. 1, 3, minus 2, 4, 0, 1, minus 1, minus 6, 0. So minus 4 plus 4 gives me 0. 2 minus 4 gives me minus 2. And minus 6 plus 24 gives me, or sorry, that's not right. Minus 6 minus 24 gives me minus 30. Okay, so you get it down to there, and the last thing you might do is you might divide through, the last thing I might do, let's kind of sneak this in, I might do minus 1 over 2 row 3 becomes the new row 3, and then this minus 2 becomes a 1, that minus 30 becomes a 15. Okay. Now, how does this help you? Well, that last row, what does that last row say? If we kind of convert back to a system, that row says 0 times, remember this is the x column, this is the y column, this is z column, these are my constants. It says 0x plus 0y plus 1z equals 15. Right? So that bottom row says z equals 15. What does the next row say? The next row says y minus z equals minus 6, or sorry, minus 6. Right? So y is equal to minus 6 plus z, which is minus 6 plus 15, which is 9. And then I can go to the first row and I can say, okay, the same as before now, right? The first row says x plus 3y minus 2z equals 4. So I plug my y and my z values in and I can solve for x and I'll get x equals 7, the same as before. Now, I chose to go this route simply to avoid fractions. The fractions weren't even bad, right? I was going to deal with kind of halves. You probably should have gone this route because I think you would end up doing about 2 fewer steps at the expense of having some fractions around. If you really want to avoid the fractions, you can sometimes avoid them by adding extra steps. Sometimes you can't avoid them at all. But this is the idea. So the idea is that we can save ourselves a little bit of writing by working with the augmented matrix instead of the system itself. So we'll explore this a little bit further in some later videos, but this will be enough for this week.